This video steps through an explanation of frequency control in electricity systems. Some elements, such as system frequency, vary across electricity systems. So in this video, I chose the wholesale electricity market, WEM, in Western Australia as the real-world reference for those elements. However, the basic concepts related to system frequency control apply universally. First, let's establish what frequency is. In alternating current electricity systems, electricity is traditionally generated by thermal generators, for example steam turbines, that use a fuel to drive a magnetized shaft that rotates inside a fixed stator, inducing an alternating voltage. The relationship between rotor speed, generator design, and the resulting electrical frequency is given by this equation. F is for electrical frequency in hertz, N is for rotational speed in revolutions per minute, P is for number of magnetic poles, always an even number. Frequency is the rate at which alternating current completes a full electrical cycle measured in hertz, that is, the number of complete cycles per second. In the WEM, as in most grids that operate on the 50 Hz standard, this means the current reverses direction 50 times every second. Alternating current is visualized as a sine wave, with the horizontal axis measuring time and the vertical axis measuring current in amps, as shown in the top chart. In ideal circumstances, the frequency of the wave is constant. This is shown in the bottom chart, where the vertical axis is measured in hertz. Note that in this simple example, the frequency remains constant as indicated by the horizontal line. In reality, the system frequency changes, which shifts the sine wave relative to its original position. The wave shifts out of step with the clock. This is called phase drift. In this example, we show the effect of a generator trip, which causes the system frequency to drop. Now suppose we then get too much generation. This causes the system frequency to rise above the target 50 Hz. Now that we have the key concepts in place, let's go back and take a look at the ideal state. We'll call this the baseline case. To make it easier and more intuitive, we can think of a wheel rolling along a perfectly smooth road. There are no bumps, so the AC waveform is smooth and the frequency is steady. Now let's introduce a pothole in the road. This reinforces the link between physical forces and electrical flow. When the wheel hits a pothole, it disturbs the AC waveform, causing a frequency deviation. Note that the system frequency dips and recovers slightly, but remains permanently below 50 Hz. This is not good in an electrical system, since it will affect every machine, slowing them down. Using the same wheel hitting a pothole analogy, let's compare a low inertia system with a high inertia system. Inertia is related to the size of rotating masses connected to the electricity system. A high inertia system will resist changes in frequency, while a low inertia system will see the frequency dip lower. So given the same number of disturbances in a system, it's better to have high inertia to control frequency. Note that inertia occurs without any discernible time lag. At this point, you may be wondering how the system frequency is returned to its target 50 Hz. Well, the primary method is to use the governor installed in electricity generators. A governor is a controller on the turbine that immediately senses changes in rotational speed and hence electrical frequency and adjusts the turbine input, for example fuel, steam, water. It operates within seconds to tens of seconds. This arrests the decline in frequency and partially restores it, but the governor's response alone is typically not enough to return frequency to exactly 50 Hz. The secondary response involves the system operator sending instructions to each machine it controls, mostly electric generators, to adjust their active power output. This occurs within a few seconds of a system disturbance. In this side-by-side comparison, a battery storage device is being instructed to inject active power. Although it's not an electric generator, it can act like one and is currently the fastest responding machine in the wholesale electricity market. In the WEM, This fast contingency response is called a Frequency Co-Optimized Essential System Service, or FCAS. This fast reaction makes battery storage devices valuable to a system operator. Of course, electricity systems experience many disturbances. In fact, there are so many disturbances that a continuous regulatory service is required. This regulation service requires controllable machines to be adjusted almost continuously. Note that in this side-by-side comparison, system frequency varies much more in the governor-only system on the left panel than in the actively managed system on the right. In the WEM, this continuous balancing service is known as Regulation FCAS, one of 5 frequency co-optimized essential system services that the market and system operator procures to keep the system stable. Okay, so I hope this helps you understand what system frequency is and how it is controlled. In recent years, fast response batteries have been added to the grid to work alongside electric generators to help maintain system frequency stability. Think back to our wheel rolling along the road. In recent years, we've added a fast-acting stabilizer to the wheel, a battery that instantly adjusts the suspension to better absorb the shock of every pothole, keeping the ride smooth for every machine on the system.